Hello. Over the past decade, a lot of companies like Amazon, Facebook, and Google have shifted away from traditional database management systems. To what and why, you ask? The answer is Hadoop. And the reason is that Hadoop is highly scalable, allowing you to store and access large datasets, the big data, across various servers and access them in real time. This is what makes it so cost-effective and also highly efficient. So, if you want to become a Hadoop developer or a big data professional, this 6-part tutorial series is the thing for you. In this introduction to Hadoop for beginners, we will go across all the components of this ecosystem of Hadoop, starting from the file storage, the HDFS, to the engine of Hadoop, which is the map reduce. You will take a look at this algorithm in action and also learn how to implement this in Java. And last but not the least, you will take a look at this really neat library called Spool. But before we get started, consider subscribing to this channel, hit that bell icon so that you get our video updates on time, and also check out our site www.OdinSchool.com. Become an OdinSchooler to stay skilled and stay ahead.
Hello everyone, welcome to the course Getting Started with Hadoop Ecosystem Core Components, and we are starting with module 1, which is HDFS concepts. So why we are learning this HDFS? HDFS is nothing but Hadoop distributed file system, and it is the core component of entire Hadoop ecosystem framework. Core components are actually HDFS and MapReduce, and HDFS is targeting a very specific problem of big data, which is nothing but the storage. HDFS is managing the distributed file system, which is actually able to store millions and billions of data, and it will prepare an environment so that our MapReduce framework can actually process this huge amount of big data. So OdinSchool. OdinSchool is a technology upskilling platform, and here we help you continuously acquire new skills. So guys, stay skilled, stay ahead. Talking about me, my name is Tushar Kakaya. I'm having 8+ years of IT experience working with various forms of data. My main skill set includes MSBI, Microsoft Business Intelligence, Hadoop ecosystem components, big data analytics using Apache Spark. I have worked with various tools like Cloudera, SQL Server Management Studio, and domain expertise is there with telecommunication domain. So in today's session, we are going to cover HDFS concepts, and we will do a deep dive into various daemons of HDFS. We will know HDFS blocks architecture and how files are fitting into this architecture. Then we will understand replication factor and how the replica placement is happening in HDFS. We will see a basic anatomy of a file read and basic anatomy of a file write whenever you are writing to HDFS. So guys, before even starting HDFS, let us understand what is Hadoop, because it's all about Hadoop distributed file system, right? So what is Hadoop? Hadoop is nothing but a specific solution. Solution for what? Solution for big data problem, and it is an open source framework. Basically, this big data problem is there currently in real world market where data is outgrowing like anything. We are using lots and lots of social media, our big size movies, images, and all those things are generating huge amount of data, and data is getting piled up, and until and unless you are getting some information from data, the data is of no use. The raw data is of no use. So basically you have to process the data. Let's say this is data. You have to do some sort of processing to generate information from this data. So you have to gain some insights from data, right? So big data is actually a problem which is divided into two categories. The categories of problems are storage and processing. Storage means how you store this humongous amount of data, and processing means how you extract information from this huge data set. And in this particular module, we are targeting basically storage problem. Hadoop is solving both of these problems, and for Hadoop ecosystem framework, basically the storage is handled by a specific component which is known as Hadoop HDFS, which is Hadoop Distributed File System. So how this entire Hadoop distributed file system is working? To understand that, let us see first what is distributed processing. In distributed processing, basically it's an approach which is very much different from centralized processing. In centralized processing, guys, what is happening? Let us say there is a single server. Let us say this is a single server, and your clients are connected to this particular server. These are nothing but your clients. So a single server is managing all the things, your storage, your processing, everything is managed by this single server. And whenever the scalability comes into the picture, that means if the client base is increasing or the data set size is increasing, at that time what you are doing, you are making this single server as a super computer, super powerful machine. Basically you are adding more RAM, more CPU cores, making that single server more powerful. And by doing this, you are basically making your system vertically scalable, right? Because here you are doing scalability vertically. But on the other hand, this particular distributed processing, how does it works? Let us see that. So in distributed processing, what will happen? You will be having several different servers or several different machines which are connected in a network. And whenever the data set is increasing, your client base is increasing, what you are doing, you are adding new node to your network. That means you are adding entire machine to your network. That means you are making your system horizontally scalable, right? Because here you are scaling your system horizontally. Okay, so this is basically the difference between centralized and distributed. In centralized, you are relying on a single machine, and if that single machine is failing, then definitely everything is failing, right? But here we are distributing the load across the networks of machines, so that you know your requests are actually distributed to multiple nodes, and no one is actually overloaded. And even if a single machine, let us say this machine got a failure in network, right? So other machines can be capable, other machines can actually handle the client request. So whenever you are having a file, let us say file1.txt, and you are having some data in it, let us say some student records or something like that, and whenever the data set is outgrowing, like file1.txt size is increasing like anything, it is really not advisable to store this single file onto a single machine or a single file system. Earlier maybe you are storing into your computer, but now it is not recommended that you store this file to your single file system, because chances of getting that particular machine got failed is high, then the data loss chances are also high, right? So you will be losing your precious data. Now here distributed file system is having an idea. Let's say your file1.txt you will store into multiple nodes. Nodes means nothing but machines over here, multiple nodes in chunks. That means you will be having something called file1_1.txt, which is having some specific records, right? Some chunks of records, then underscore 2.txt underscore 3.txt. So this way, basically, you are dividing your file1.txt and storing into separate nodes. And this is how the distributed file system is working. As you can see here, the nodes are connected in a network. They are forming a network. So all the complications which are there in network programming, that will also come into the picture. Like how you will handle the network failure, how your system would be reliable, because everything over here, let us say I'm telling about these nodes, then those nodes are commodity hardware. Commodity hardware means nothing but common configuration hardware, where you are not having fancy hardware like RAM, CPU cores. Basically it would be a common capabilities hardware. My computer is having 16 GB of RAM, a dual core processor maybe, then it can very well work, or it can very well be added as a node to my existing distributed file system. So that is possible. But at the same time, when you are doing this commodity hardware concept, at the same time you are actually at risk, right? Because these are the common configuration hardware, and it can fail anytime. So that is kind of a challenge, and that is what is handled by HDFS. How it is handling, we will see in further slides. But these are the complications which are coming up in the network programming, and Hadoop distributed file system has to deal with it. So let's start with the design of HDFS. So HDFS is actually designed for very large files. Large files as in like files which are of size megabytes, even gigabytes, terabytes. So these are like ideal pick for HDFS. To store this huge amount of data, HDFS is actually designed for. Here this very large context means files that are these MBs of or GBs or TBs of size are actually supporting the design of Hadoop as well. Like Hadoop is targeting this big data problem, right? So that's where this thing come into the picture. Big data, huge amount of data. HDFS is actually designed for streaming data access. Streaming data access means it is built around the idea that the most efficient data processing pattern would be write once and reading many times. So let us say you are having a source from where you copied the file to HDFS. Then you are writing to HDFS one time. Then many users would be able to read that particular file over the time. Okay, so reading many times, many users will read many times, but you are writing once only on HDFS. So here basically we are talking about streaming data access. At the same time, HDFS is designed using commodity hardware concept in mind. That means actually entire Hadoop doesn't require expensive or highly reliable hardware. It is actually designed to run on clusters of commodity hardware. That means commonly available hardware that can be obtained from multiple vendors. Okay, that is completely fine. For which the chances of node failure across the cluster would be again high. Okay, so definitely this commodity hardware is coming up with its own cost. Like whenever you are using a commodity hardware, the chances of it getting failed would be high. That means HDFS is should be that much intelligent, so that there would be some very negligible interruption to the user in case of such failure. And yes, HDFS is designed for this kind of commodity hardware, and it does support this kind of transparency to the user, so that as at a user level you will not notice a significant amount of delay or interruption in case of such failures. Then let us see, HDFS is not a good fit for which kind of applications. It's not always that your application would fit into HDFS architecture. HDFS is designed for some specific things in the architecture. So these are the things which are not a good fit for HDFS. And the very first one here is low latency data access. Before we start with that thing, let us study what is difference between latency and throughput. These are the two keywords which would be very useful when we are learning any file system or any network based programming concepts. So what is latency? Latency means nothing but the time required to do some task, basically. right? And throughput means nothing but over a period of time, what amount of work you are doing. It is the task which you are doing, and latency means to do a particular task, what is the time required. That means latency would be always measured in unit of time, like milliseconds, seconds, even sometimes hours or days, right? So over here, I would try to explain you this latency versus throughput with a specific example of a water pipe. Whenever you are trying to buy a water pipe, you will see, two independent parameters of the pipe. Let us say this is your pipe. Let us say this is your pipe. Then you will see what is the diameter of that pipe. Diameter means what amount of water can actually go at one time. Okay, what amount of water can actually be be passed to this particular water pipe is what known as throughput. So it is amount of water which is going in a particular time. Okay, and latency, what do you mean by latency? Latency means nothing but time required to travel water from one end of the pipe to the second end of the pipe, and that is nothing but the latency. Let us say it is taking 5 minutes, or let us say 5 seconds, whatever it is, depends on the length of the pipe. So that time period is known as latency. So here you always have to remember that in HDFS, retrieving whole data set at one time is more important rather than retrieving the first record of that file. So let us say there is a file which is having like 100 millions of record. So here the throughput, that means retrieving entire 100 million records at once and performing analysis on top of that is more important rather than retrieving only the very first record from these 100 million records. That would be taking time. Retrieving first record would definitely take the time. But we are not interested in that. When we are talking about HDFS, we are actually dealing with big data. We try to you know process the entire table or entire file altogether rather than a single record. Okay, that's what I'm trying to explain over here. So here HDFS is delivering this higher throughput, but at an expense of latency. Okay, then the second concept come over here is lots of small files. Whenever we are learning HDFS on a pseudo distributed machine, that is fine. You are having small files, like having only few records, and the file size in kbs, then that should be fine because you are learning. But in real time, in production environment, whenever you are storing these small files on HDFS, at that time there is a problem associated with it. The problem is, whatever file, let us say you are having a file 1.txt, then that file's metadata means all the information about that particular file, like its permission, where it is stored, how much part it is, how much how much division is happened at granular level. So all these details are actually stored in name node's main memory, which is RAM. Name node is a machine or a daemon of HDFS, which we will study in subsequent slides. But that name node is a very kind of a master machine or master in this particular HDFS architecture. And if name node's RAM is getting full, then that would be a problem for the entire cluster, for the entire HDFS. So definitely the metadata of a particular file, if it increases then the actual file size, then there is a problem because name node is storing everything in its RAM, in its memory. So definitely the limit to the number of files in the file system is governed by the amount of memory on the name node, right? So that is the reason it is not advisable to store lots and lots of small files, because the small file, each and every file will have their metadata, which is even higher than the actual file size. So it's not a wise practice. And the third one is multiple writers and arbitrary file modification. So files in HDFS may be written by a single writer, right? And writes are always made at the end of a file. So let us say you are having a file, then writing new thing would be always happen at the end of the file, and that would be append only fashion. So there is no support for multiple writers, multiple user writing at the same time on HDFS, or for arbitrary modification, like you are trying to modify a record in between at arbitrary location, at arbitrary offset in the file. This might be supported in the future, but they are likely to be relatively inefficient in this particular concept, and it is not a good fit for HDFS. So now let us understand what exactly is HDFS block and what is the block size. So block is nothing but a small unit in the file system, the block, what you say, like a small chunk or small portion of the file system where the data would actually be stored. And block size is nothing but the minimum amount of data it can read or write at one instance, right? So if you see the block size in Hadoop release 1, so HDFS was supporting 64 MB. That was the default block size for Hadoop release 1. But 64 MB only you can read and write at one single time, right? So now from Hadoop release 2, they have increased this block size, and they have exactly doubled this block size, and that is now 128 MB. So what exactly would happen? So whenever a file, let us say this is your again file 1.txt, which is having, let us say, 260 MB size. Okay, so what will happen? It will try to divide and accommodate into this 128 MB size blocks. So if you see 128 MB block, then from this 260 MB, 128 MB would be divided, or that chunk would be stored in, let us say, block number 1. Then remaining 128 MB would be stored at block number 2. So 128 and 128, which means it is having, let us say, 256 MBs worth of data already divided and stored to multiple blocks. So now 4 MB remaining, right? So this 4 MB would be stored in another block B3, and if you see, still 124 MB left for block 3, and that would be not reserved for this particular file1.txt. You can actually store any other file also to this particular remaining space. So in real time, it may happen a block can consist of so many different file chunks, and whatever data you are storing to blocks, so this data to block location mapping would be again stored in one of the daemon of HDFS, which is nothing but Namenode. So we'll study that particular thing also in depth in our next slides. So what I want to tell you, like your particular file would be divided into several chunks depending on the free block size on your HDFS, and then it would be stored to multiple locations. Now, what do you mean by multiple location? That means it may happen block 1 and block 2, they are part of a particular machine named node 1, and block 3 can be part of a different machine altogether, which is node 2. So what exactly this topology is, let us try to understand that one. So here in HDFS, or even you can say this Hadoop ecosystem, we are having some terms which we need to understand. The very first one is nothing but the node. Node means nothing but a single physical machine with its resources like RAM, CPU cores, hard disk. Okay, so that is nothing but a node. Node means nothing but a machine, you can say, right? And several node, let us say this is node 1, then we are having node 2, node 3, node 4, and all these nodes in a network prepare a rack. So rack will have several nodes in it, and rack would be kind of a clubbing of nodes at one physical location, right? So let us say a rack is there at India location, so you will be having all the nodes inside that rack at one single physical location. Now we are having several racks like this: rack 1, rack 2, rack 3, and combination of all the racks would prepare a cluster for Hadoop. So cluster is made up of racks. Racks are made up of nodes. Now here these racks can be at different physical location as well to form a cluster. You know, so let us say you are having a cluster for your banking application, then it may happen one rack is there at, let us say, India branch, and inside that Mumbai location, where so many nodes are there. So let us assume the bank is having 6 branches in India. One is at Hyderabad location, one is, let us say, Gurgaon location. So this way, each branch is having their racks, and all these racks are communicating and forming a cluster. It may happen some racks are even out of India. That is also fine. But my main point which I want to clear is racks can be at different physical location. But inside a rack, all the nodes would be at one physical location. So, keeping this in mind, let us see the daemons of HDFS. So, there are 4 daemons of HDFS. The very first one is name node. The second one is secondary name node. The third one, which was introduced in Hadoop release 2, which is nothing but standby name node. And the fourth one is data node. So here, HDFS is always working in master slave topology or master server architecture, where one master would be like managing all the slaves. Here, name node is nothing but the master node or master daemon of HDFS. What name node is doing? Name node is managing a file system namespace. Now, what is the namespace? Namespace means nothing but entire tree of your file system. Let us say in my file, I am having a C drive. In Windows, I am particularly talking about. Then inside the C drive, I am having, let us say, a users folder. Inside users folder, I am having a Tushar K folder. Inside that, I am having my documents. And inside that I'm having some file, let's say 1.txt. So at a file system level, you can see C drive is nothing but the root node. On this root node, we are having several branches. On one branch again, we are having several other children branches, and likewise ultimately your file would be stored. So this entire file system tree is nothing but known as namespace. Now, name node is managing this entire file system namespace. So it will maintain the file system tree, and also it will maintain the metadata, basically the metadata of all the files and even the directories in this particular tree. Metadata means any information about the file. And this information is stored persistently on the local disk in the form of 2 files. The very first one is namespace image and second one is edit log. Namespace image means kind of a snapshot, you can say, what exactly the situation is currently at your file system level. That particular snapshot is nothing but namespace image. And edit log means if you are adding a new file, if you are removing some directory, if you are modifying some directory, let us say this Tushar K is completely removed. So those are nothing but the edit logs which it has to apply to the namespace image, so that you will have up-to-date snapshot of your file system every time. Name node is having another task, which is managing the data nodes. Now, name node also knows data nodes on which all the blocks for a given file are located. I just explained you, right? Like a file would be actually stored to multiple blocks, and those multiple blocks can be at different nodes. So data nodes are ultimately where the data is actually stored. So name node knows which data node contains which blocks and which file is actually mapped to which blocks. So this file to block mapping is actually a duty of name node managing all these things. Okay, then comes into the picture is a secondary name node. So what exactly the secondary name node is? Secondary name node is kind of a backup for the name node. It merges the namespace image with the edit log time to time, right? So edit log would also be there with it. Okay, so it will merge to the namespace image and it will tell, like, let us say this example, then Tushar K is deleted. So then it will merge to the namespace image, and then you will be having C drive users only in your latest snapshot. But secondary name node is also kind of a master name node, not name node, but you can say it is a master node. So it is always advisable to run it on a separate machine, and it will require same hardware configuration like name node, because it is ultimately nothing but the kind of a backup for name node. So whatever hardware configuration you are giving for name node, you should give for secondary name node. And all these guys, all these nodes or daemons are master, acting as a master. So you should give slightly better configuration for this kind of daemons, like name node, secondary name node. Okay, it should have more RAM, because if you see this metadata is always stored in name nodes in memory. So you will give more RAM compared to data node to this particular daemons. Then it will be helpful. Secondary name node would be actually taking backup. Why? Because if you see still in our architecture, like name node is master, and if master is failing for some reason, name node is actually down, if that machine is down. And that is again one of the reason why you should actually give more RAM or better configuration hardware to your name node. So uh, basically, if the master fails, then in that case, imagine like all your file to block mapping is also gone, right? That is not accessible. So if client is trying to read a data or read a file which actually is stored at different location, and you need to club them together to give client a transparent snapshot of the file, transparent read of the file. So that won't be possible, because your data to block mapping is gone, because the name node is down, and the entire Hadoop ecosystem is down, because where the file ultimately the data is lost. So even MapReduce won't work in that case. So in this kind of failure event, secondary name node would help you to give you the logs and all, because it is having at least like edit logs which are merged into namespace image. So it will be able to give you the current snapshot of the system or file system namespace, and then you can recover from it. Of course, whenever you are recovering, then your system would be down at that time, right? So downtime is definitely there. And even secondary name node will not have up to date snapshot, because name node is managing all these things simultaneously or continuously. But in secondary name node there is always a lag. So during that lag, if something happened, like this Tushar K directory was removed, after the name node gone down, then definitely you will not have the up-to-date snapshot, because the secondary name node is not having that log still. And that particular reason would make this HDFS as a not highly available file system. It is not having that highly available file system property. So secondary name node, again I'm repeating, secondary name node cannot act as a name node. It is just for the backup purposes. Whenever the failure occurs for name node, some data loss is certain, because the secondary name node's state is lagging of that of the primary, which is the master name node. So what is the solution for that higher availability of the HDFS? And the answer is standby name node. And the answer is standby name node, which is introduced in Hadoop release 2 for name node higher availability. So basically there would be some pair of name nodes, which is like active and standby mechanism. Whenever the failure of the active name node occurs, the standby would actually take over its duty, and mostly it would be transparent to the client, and it would be happening without any interruption or a little bit of delay, which is negligible. So that is one, again, one important daemon, kind of a master for this particular architecture. And the slave is nothing but data nodes. Data nodes can be as many as you want depending upon the data you want to store in your HDFS, and it is a slave for this architecture. So as I told you, it can be as many as you want and can be increased also to make your system horizontally scalable. They are storing and they also retrieve the blocks whenever they are told to by client itself. So client can, let us say this is your client, it can directly communicate with data node, or it can actually communicate with name node, and name node will again communicate with actual data node where the data is stored. So data nodes one duty is to store the data basically, and it will also send some heartbeat signal to name node saying that I'm alive, and what all the blocks I'm having currently, so that the name node will be having up to date file to block mapping list. So it reports back to the name node periodically with lists of block that they are storing, and that is known as the heartbeat signal. So this is kind of a high level diagram where you can see there is a master, there is a slave, and slaves are nothing but data nodes basically. Um, and you can have up to n data nodes, right? And then master, you can say there is a name node, there is a secondary name node. The name node is actually maintaining the metadata of data node 1, data node 2, data node 3, and data node 1 is having like block A and C, then data node 2 is having A and C, data node 3 is also having A and C. I'll tell you why these blocks are replicated in the further slides. Then secondary name node, if you see, it is maintaining this file system image and edit logs. Okay, so all these things which we have discussed till now. Again, a diagram at higher level for HDFS architecture. So let us say there is a client which is actually trying to read data from data nodes. So data nodes can actually have some blocks like this. They can read the data and give it the result to the client. Then client is doing some metadata ops to the name node, where the metadata like name, then how many replicas are there, then this kind of directory trees. Let us say this nothing but him, foo, data, these are the folders at Linux level, and then there would be some block operations which it would perform on the data nodes, and data nodes are having some concept of replication where it will replicate the data which it is having to other data nodes or on the same rack, which we'll study later on. Then again, client can actually communicate with data node, as I told you, to write the data directly, and this is kind of a rack 1, which this is nothing but rack 2. Okay, so this is about the HDFS architecture. This is again one architecture diagram where you can see HDFS client is doing some metadata operations with a name node, secondary name node, and it can directly communicate with data nodes, and data nodes are actually doing replications for load balancing as well. So we will study somewhat in depth about the making name node resilient to failure. That is about the standby name node, right? That is something newly introduced in Hadoop release 2. So basically, whenever the name node failure happens, to protect the data, what we can do, we can replicate the name node metadata on multiple file system. That means whatever name node, let us say name node is storing this file system image, the namespace image and the edit logs and all those things. things to its hard disk, then we will try to replicate those files to multiple file system. Let us say on cloud 1, cloud 2 URL, cloud 3 URL, like that. We can try to replicate that data to multiple file system, so that if the name node is down, then we can retrieve those files from this cloud based system, or shared based systems. And you can actually use the secondary name node to create this kind of checkpointing also. But that will really not provide you the higher availability, right? Because what will happen ultimately, whenever the name node fails, this checkpointing happens, let us say, every 5 minutes. So at 5 it happened, and then again it will happen at 5:05. And what if the name node is down at 5:03? So this 3 minute worth of records or data won't be there in those files, right? So definitely some data loss is certain in this scenario. And that is the reason you can say Hadoop release 1 was having a single point of failure, SPOF, which is nothing but the name node. To get rid of this bottleneck, what exactly they have come up with, right? What is the solution? The name nodes must use highly available shared storage to share the edit log. So whenever it is storing something in its edit log, that edit log would be shared across multiple nodes. So multiple nodes, by that I'm meaning to standby nodes. So whenever a standby name node comes up, let us say name node is down, this is your active name node, let us say it is down, then the standby would come into the picture, standby name node. So it will be having up to date information about the edit log, okay, because it is shared with it, and it can actually try to synchronize its state with the active name node. So then you just need to redirect your client so that clients can route to simply standby name node rather than active name node. You just active name node rather than active name node, you just need to redirect to the standby name node. So that what will happen, client will read data from standby name node, okay, and standby would be nothing but your new active now, okay. And your data nodes you have to configure like that also, right? So your data node 1, 2, all these data nodes also need to uh, you know send this heartbeat signal to standby name node rather than the active name node. So there is a shift, basically a pointer is changing now, you can see that, okay. So that is what HDFS high availability is, and that is how you can get rid of this SPOF, single point of failure. And in order to do that, you have to configure your clients like that so that they can handle this name node failover transparently. Then standby name node also does the work done by the secondary name node. You can see that, right? That, like, they are also taking this checkpointing backup, and also standby name node should also have the higher configuration like a primary name node. And if the active name node fails, the standby can take over very quickly in a few tens of seconds ideally, because it will be having latest state available in memory, both the things like edit log entries and up to date file to block mapping. But trust me guys, the actual observed failover time will be longer in practice, sometimes around a minute or so, right? So because the system needs to be very conservative also, right? Like the active name node has failed, it has to just confirm that thing, then only it can make the new standby name node as active. So during that time, slightly you can see there is a slowdown, or you can say downtime there in your cluster. So this is just for your information, like nothing is always ideal as it seems. Then let me introduce you some architectural terms for HDFS. The very first one we have already seen, which is namespace, which is kind of a hierarchy of files and directories. Then we will be having something called inodes, okay. So basically the HDFS namespace is a hierarchy of files and directories, right? Now files and directories are represented on the name node by the inode. Like, let us say in our Linux file system, let us say this is a root folder. Inside the root folder you are having subdirectories or subfolders, which is having like home, then etc folder, then user folder, something like that, right? So uh, here the files and directories are represented on the name node by inodes. So inode will be having some attribute like the permission, who can access the directory or file, modification time, last access time, then namespace and disk space quotas, etc. Then the term comes like image and checkpoint. So inodes and the list of blocks that define the metadata of the name system are called nothing but the image. Image is nothing but kind of a current snapshot. Okay, and always name node will keep this entire namespace image in the RAM. Okay, now the persistent record of the image, that means one which is like permanent, which would be stored in name node's local native file system, which is called a checkpoint. That means after some point of time, if you are sure that directory is there, then it will store to its hard disk, which is nothing but the checkpoint. And there is a journal which is kind of a whatever changes which are happening to HDFS directory tree, and you are recording those changes in a write ahead log, and that is called journal, which would be stored again in the local native file system. Then let us study a very important concept in HDFS, which is nothing but the block caching. Caching means whatever you are using or reading frequently, that you should store at separate area so that it can be quickly accessed, and the read time for your data would be considerably lower than whatever otherwise you are reading from. So normally a data node will read the blocks from the disk, right? From the hard disk or the local native file system of that particular data node, which is again a machine only, right? But for frequently accessed files, the blocks may be explicitly cached in data nodes in memory, which is like again a off heap kind of a block cache. Okay, so by default, a block is cached in only one data node's memory. Although the number is you can something which you can configure on a per file basis. So job schedulers for let us say MapReduce or Spark or any other framework which is processing your data, it can actually take some advantage of these cached blocks so that it doesn't have to simply read the data from the hard disk and again store to the RAM, right? Because generally what happens, your data is, let us say, stored to this kind of a hard disk. It will be then pushed to the RAM, and then from RAM the processing engines like MapReduce or Spark is reading the data. But this particular step is totally bypassed because your data is already there in the RAM. Okay, so that is what the block caching is, or the caching is simply any small lookup table. You can say a small lookup table like let us say you are having employee data set which is having employee id, department id, salary, city, etc. So department id is having like 1 2 3 4, and then you need to join with a department table, right? This department table where the mapping of one first department id is mapped to, let us say, HR, second one is finance, like this. Which department it is, department id to department name, that mapping is stored into some small table, because you are having, let us say, 10 department, then department table would be having only 10 records. So this kind of small lookup table, which you frequently need to join, right? Because whenever you want thorough employee data, then department id is of no sense, because a particular person with department id 1, what actually it refers to, the one is actually HR department. That means that employee is working to HR department, and that is how the linking is there between this employee and department table. So this kind of lookup tables are again a good candidate for the caching. So users or applications basically, they will try to instruct the name node which files to cache, and for how long you need to cache, and they will add to some cache directories okay, or caching queue or cache pool. And cache pools are an administrative grouping for managing cache permissions and resource usage. So definitely your DFS client should be also scheduled for memory locality. Then cache commands, they will piggyback on the heartbeat response, and this way the data node will again heartbeats that will contain the cache block reports as well. Okay, data node's heartbeats would also contain cache block report. So this is how this entire block caching is working. Then let us discuss about HDFS Federation, which is again introduced in Hadoop release 2. So basically your name node is simply maintaining the reference to the every file and their block mapping, right? And that is in memory. In memory means it's in RAM. And when we are telling like it is in RAM, definitely your name node should be having higher configuration RAM. But when we are talking about this kind of Hadoop distributed architecture where commodity hardware is the key for this ecosystem, then definitely chances of getting it failed is high, right? So when you are growing, when your cluster is growing, your number of data nodes are growing, your directory tree is growing, at that time memory is really a limiting factor for scaling. So to remove this limitation, basically HDFS Federation was introduced in the 2.x release. Now it will allow the cluster to scale by adding more name nodes. Okay, now this is something different than your standby name node or a secondary name node. You are adding more name node, and each one of them will manage a portion of the file system namespace. So and this namespace, let us say you are having a data node 1, this is data node 2, data node n, so they are having kind of a block pools. Every pool would be managed by a different name nodes, and this name node will not interact with each other. They are independent of each other, they do not communicate with each other, and failure of one would not affect to the failure of others. Sorry, failure of one would not affect others. So how this thing would be working, let us say you are having a root directory. Inside root directory, let us say you are having user directory, you are having a tmp directory, you are having etc directory, like this. Then root user and all the subdirectories would be managed by name node 1. Then root tmp, inside that whatever file directories are there, that would be managed by name node 2. Then root etc, all the directories or files under that would be managed by name node n, let us say. So this way directories would be divided. So inside the directory whatever is happening, that should be managed by a particular name node. And that is how the HDFS Federation is working. Then let us discuss about the replication factor and how the replica is placed. So basically, replica is all about data nodes data. So we have seen how we can handle the failure of name node using secondary name node or standby name node, right? That is all about metadata. But what about actual data? If the actual data is lost, or a particular data node where the actual data is stored, and if that data node is gone, and chances of that is getting lost or that is getting failed is very higher, right? Because they are having even less configuration than your master nodes. So definitely HDFS needs to ensure against the corrupted blocks and even the disk and machine failure for the data nodes. For that, each block is replicated to a small number of physically separate machine, and typically by default it would be 3. That means the replication factor is 3 by default. If a block becomes unavailable, then you can actually copy or a copy of it can be read from another location, because it is replicated thrice, not twice. That would be replicated thrice. And then you again need to ensure that that replication factor should back to the normal level of 3, so that you need to again copy to somewhere else so that the replication factor is 3. So whenever it is lost, you can actually get a copy from somewhere else, and then again you need to make another copy so that the replication factor is back to 3. For some applications which are very sensitive, which are like banking client data, or something which is very crucial, so for those kind of application, even higher replication factor for the blocks, for some popular files which you can't afford to lose, that is set. So higher replication factor is allowed, you can actually configure it, okay, and that would be replicated multiple times. Even I have seen some files are replicated 10 times also to different data nodes, so that is also possible. But here always a trade-off comes, trade-off between the reliability and the write bandwidth and the read bandwidth. Okay, so what are the possible options to place these replicas? That is what we are going to discuss over here. So placing all the replicas on a single node, that is actually a good thing and a bad thing also. So let us try to understand. Let us say you are having your block one, that is replicated uh, three times b1 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 on a single node which is n1. Now if one block copy is lost due to some partition failure for that disk, other two are still there, you can get a copy from it, okay. But what if this node 1 got failed? Okay, so whenever this kind of situation will occur, two things are there, okay. The first one, the advantage is like you are having lowest write bandwidth penalty. That means b1, all the b1 blocks are in the same node, are on the same machine. So what is the advantage? You can get a copy with negligible bandwidth delay, right? Because it is on the same machine. So same machine, copy to copy is really not that much worrisome task. But the disadvantage is if the node 1 fails, then you are losing all the three blocks, which is not ideal, right? So basically you are not making your system reliable over here. So this will not offer you any real-time redundancy. Okay, if the node fails, the data for that block is completely lost. Now what exactly we can do, you can actually try to place these replicas on a different nodes as well. Okay, so let us say there is a rack r1 which is having node 1, node 2, node 3, node 4. So block 1, one copy is at node 1, one copy is at node 3, and one copy at block 1's one copy is at node 4. Now if even if the node 1 fails, you are still having your block 1 to n3 and n4, which are on the same rack. So again, if the block 1 all the copies was at the same node, then definitely the reading and writing bandwidth would be faster, but at the same time you are losing on the reliability. But now they are on the different nodes, so definitely the reading and writing would be somewhat time consuming, but definitely you are reliable, your system is reliable, so that your data can be retrieved from different blocks. Of course the time it would take to copy from node 3 now, that would be higher because it is at different node, but still they are in the same rack. So again they are in the same physical network, because racks, as you remember, that they are having nodes at the same physical location. Now imagine this rack 1 got failed. Rack 1 got failed, that means all the copies of all the nodes, completely lost. So in that particular time, how can you make your system reliable? For that, again, we are having an option. Let us say this is your rack 1, this is your rack 2, this is having node 1, 2, and 3, let us say. This is having node 4, node 5, node 6, let us say. This is having block 1. Keep one copy in the same rack, but keep the third copy at different rack. So in case the rack 1 even fails, if rack 1 fails, rack 2 is still having one copy, which can be helpful in case of data recovery. So generally this is how the replica is placed. Here, keeping a copy on rack 2 will actually make the read and write more slower, because maybe this is at India location, this is at Australia location. So definitely the delay in reading and writing, those things would be coming into the picture, but you are having your data. So always a trade-off, as I told you, between the reliability and the write bandwidth and the read bandwidth. So that is what explained over here. You can see Hadoop's default strategy to place the first replica on the same node as the client. So wherever the client is, okay, put the data on the same node so that your client can actually read or write in a faster way. But if the client is running outside the cluster, then definitely your node would be chosen at random. And here if you see, as I told you, anything can be fine. Okay, basically two replicas on the one rack and one is at off rack. So this is known as off rack, where you can see second replica is placed on a different rack from the first. Let us say this is your R1, this is your R2. Then the second replica is placed off rack, chosen at random, and the third replica is again placed on the same rack, because you want to achieve that read and write bandwidth also. So that is completely fine, choose at random but on the same rack. And if you are again having replication factor greater than 3, then you can place further replicas on random nodes in the cluster. The system tries to avoid placing too many replicas on the same rack. So definitely good balance among the reliability, write bandwidth, read performance, block distribution across the cluster. Basically over here in HDFS, they try to see no single data node is overloaded. They will try to balance the things. Okay, they will try to do a load balancing so that the data can be read and write from different nodes. At the same time, the bandwidth is also not coming into the picture, and at the same time your system is more reliable. Now let us discuss the data flow, like how the data flows whenever a client is asking to reading a file. Basically anatomy of a file read. So this is at higher level what happening, described in 6 steps. The first one is opening the connection, second one is getting the block location from the name node, because ultimately name node knows, right, like which file consists of which block. That means the file to block mapping. Then again you will be seeing a read connection established with file system data input stream, which is a Java class again, and then reading the file from different data nodes. Let us say multiple data nodes are there, then that would be happening. And then the sixth step is nothing but the closing the connection. So let me try to just give you an overview what exactly happening in these 6 steps in detail. So the very first thing is client is opening the file. It wishes to read by calling the open method, which is kind of a Java method, because everything over here is implemented in Java, right? So open method on the file system object, uh, which for HDFS is nothing but kind of an instance of the distributed file system. Distributed file system, DFS instance, is nothing but the file system. So distributed file system calls the name node first, right? In the second step, if you see, it will call the name node using some kind of remote procedure calls, RPCs, to determine the location of the first few blocks in the file. For each and every block, the name node will return the address of the data node that have a copy of that block. So name node will tell something like file one's block number 5 is at data node number 6, something like this at higher level. So you know now at which data node, at which block your file is. That address is there with you. So furthermore, the data nodes are sorted according to their proximity to the client, how near they are to the client, and that all the things would determine the bandwidth, how quickly you can read the data or write the data. So definitely client is asking, let us say block number 5, so data node 6, wherever it is, okay, but chances would be there like name node has that intelligence, so that it will try to store to the nearest proximity to the client, because if a client is of India, then there is no there is no mean to store the primary data block to Australia rack. Okay, so that those kind of things would be taken care of by the name node whenever it is storing the data. Whenever first client had asked it to write, at that time these things would have been considered by the name node. So if the client is itself a data node, that is also one case, right? For example, MapReduce task. So the client will read from the local data node itself. Okay, uh, if that data node host is having a copy of that block. So the distributed file system will always return you a FS data input stream object, which is kind of a input stream that supports the file seek operation, and that would be written to the client so that it can read the data from FS data input stream. In turn, will wrap the DFS input stream only, which manages the data node and name nodes input output. Then client will call the read method on this FS data input stream object. Now, DFS input stream, which has stored the data node addresses for the first few blocks in the file, that will connect to the closest data node wherever that copy is. Okay, and data is streamed from the data node back to the client, which is calling the read method. And this would be repeatedly happening in a stream means a kind of a pipeline. Okay, and then when the end of the block is reached, DFS input stream will close the connection to the data node first, then find the best data node for the next block. This happens very transparently to the client, so that client is having kind of a single view that it is reading in a continuous stream, but ultimately it is series of streams with different data nodes. Okay, and these blocks are always read in order, with the DFS input stream opening the new connection to the data nodes as the client is reading through the stream. It will also call the name node to retrieve the data node location for the next batch of blocks as needed, because for first few blocks it has given the address, right? So for the next few blocks again it has to ask for the address. So this way, whenever you are getting the block location, try to read in a stream. Okay, then the next block location, next stream, something like series of streams, right? And when the client has finished reading all these things, it will call the close method on the FS data input stream. So during reading, if the DFS input stream encounters an error while communicating with a data node, then what it will do, it will try the next closest one for that block. And that is the reason we are storing, two copies on the same rack, so that the speed of reading would be nearly identical, because it is still on the same rack, same physical location. So it will try to read data from the next closest one for that block. It will also remember data nodes that have failed, so that it doesn't needlessly retry them for later blocks. The DFS input stream also verifies checksums uh, for the data which are transferred it from the data node. And checksum method is nothing but kind of a method where you will see the checksum answer while writing and while reading are coming same, so that the file is not tempered or modified. It's the same file which you have written, and the same is read by the client. If a corrupted block is found, definitely the DFS input stream will attempt to read again a replica of the block from another data node. Okay, and it will also report to the name node like this block is corrupted, something like that. Now what happens, what kind of data flow happens whenever you are writing the file, whenever client is writing a new file? Basically, what is the anatomy of a file write? So again, here you can see 7 steps at higher level. The first one is create, second one is creating to the name node, because whenever you are creating a file, the metadata should also be created. So name node will also get the request. Then write method is there, and here you can see fs data output stream. Over there you were able to see fs data input stream. So after that, writing down in a packet, basically we will see some queues are there, write packet queue, acknowledgement packet queue, and the data would be written to various data nodes according to the free space, and then complete and then close. Sorry, then close and then complete. So let us see all these steps in detail. So here at the very first step, the client will create the file by calling the create method on distributed file system. Then the distributed file system will make an RPC call to the name node to create a new file, basically in the file system's namespace. Right, in the namespace also you should create a new file. Uh, at the very first time, whenever it is creating the new file in file system's namespace, there would be no blocks associated with it, because you don't know, right, like what would be the file size and all those things. So the name node is actually performing various checks also to make sure the file doesn't already exist. Then the client has the right permission to create the file. All those things would be happening as a part of the checks. Now if the checks are passed, then the name node makes you know a record of the new file. Otherwise file creation would be failing, and client would be having kind of an IO exception, or file no, file already exists exception. All those kind of error handling would be happening. Then the distributed file system returns an fs data output stream object for the client to start writing data to. Okay, uh, just as in the read case, I had told you, right, like fs data output stream is wrapping a dfs output stream in turn. Okay, now as the client writes data, the dfs output stream splits it into packets, which it writes to an internal queue called data queue. Data queue is something which is consumed by the data streamer, which is responsible for asking name node to allocate new blocks by picking a list of suitable data nodes to store the replicas. Basically, whenever a new file will come, right, let us say this file 1, then how much file size is there, you divide it into blocks, and then those blocks should be written to which data nodes. All those things would be asked to name node, and name node will give you response based on the data queues blocks or packets. Then the data streamer will stream the packets to the first data node in the pipeline, which stores each packet and forwards it to the second data node in the pipeline. Similarly, the second data node stores the packet and forward it to the third and the last, basically, data node in the pipeline. Here there is a concept of acknowledgement queue as well. So DFS output stream acknowledgement queue is also there. If dfs.namenode.replication.minimum replica, that is a property, if that is having a value 1, that means you are having 3 replicas, right? But if first one is written, then go ahead, then write is actually succeeded, and subsequent blocks, like 2 blocks are still remaining, right, they would be asynchronously replicated across the cluster until the target replication factor is reached. But if the first one is written, then the write will succeed. Okay, you can go ahead like that. And once you are finished writing the data, it will close the connection to the stream. And whenever you are closing, this action will flushes out all the remaining packets to the data node pipeline and waits for the acknowledgements before contacting the name node to signal that the file write is complete. So guys, in today's module we have seen like HDFS concepts, and we did a deep dive into various daemons of HDMS. So guys, in today's session, what we have seen, let us quickly revise. We have seen HDFS concepts. We deep dive into various daemons of HDFS. Now you should probably know what exactly the block size is and how this block architecture is coming into the picture and how the files are fitting into that. We tried to understand the replication factor, replica placement topologies, and we did a detailed anatomy of a file read and a file write. So thank you very much, guys. Don't forget to like and subscribe to our channel. Thank you.